welcome to The Explainer. All right, today we're diving into one of the gnarliest problems in modern software: why our apps sometimes break in these really strange, unpredictable ways. It's time to tame the chaos.
You know the feeling, right? You've got this super powerful computer, you're running an app you've used 1,000 times, and then, boom, it just freezes. Or it starts acting weird. And you're sitting there thinking, it can't be a lack of power. And you're right, it's something way more subtle happening under the hood. And that something is a real double-edged sword called concurrency. It's the secret sauce that makes modern software feel so slick and responsive, letting it juggle a dozen tasks all at once. But here's the catch: that exact same power is also the source of some of the most frustrating, hard-to-pin-down bugs you'll ever encounter. And this isn't some niche issue. Check out this quote from Intel's Doron Rajwan. He's basically saying, the game has completely changed. For decades, it was all about Moore's law, just making a single processor faster and faster. But we've kind of hit a wall there. Now it's all about Amdahl's law, which is really just a fancy way of asking, how good are you at splitting up work across all the multiple processors we have? Okay, so to really get this, we gotta understand the difference between a process and a thread. A process is like a self-contained house. It has its own walls, its own furniture, its own memory. Running two separate apps is like having two separate houses. But threads? Threads are like roommates living inside that same house. They share the kitchen, the living room, they share the memory. And because they share everything, they can communicate and work together incredibly fast. But you can see where this is going, can't you? That whole sharing everything idea, that's exactly where the danger comes in. It's like having three roommates all trying to write on the same grocery list on the fridge at the exact same time. Without some serious rules, you're pretty much guaranteed to end up with chaos.
So let's dig into the most common kind of chaos you'll run into. It's called a race condition. And honestly, the best way to wrap your head around it is with this brilliant analogy from the book Java Concurrency in Practice.
Okay, picture this. You and a friend make a plan. Let's meet at noon at the Starbucks on University Avenue. Sounds foolproof, right? But then you get there and, oh no, there are two Starbucks on University Avenue, one on each side of the street, and you never specified which one. The race is officially on. So you do the logical thing. You pop into Starbucks A. No friend. Okay, you think, they must be at the other one. So you start walking to Starbucks B. But here's the kicker. While you're walking, your friend shows up at Starbucks A. You get to B, they aren't there. You've both been to both locations, you've both done the right thing, but you've completely missed each other. Your timing was just perfectly, disastrously wrong.
And that right there is a classic race condition. The success of your program, in this case meeting your friend, depended entirely on the unlucky timing, the interleaving of your actions. In software, this is when two threads race to use the same resource, and depending on which one gets there a millisecond first, the entire outcome can be dead wrong. This specific pattern has a name. It's a check, then act error. Think about it. You checked a condition, is my friend at Starbucks A, and then you acted on that information. The problem was the world had already changed between your check and your act. The information you had was stale, it was out of date, and this seemingly logical pattern is the root cause of an incredible number of concurrency bugs. Okay, so a race condition is bad. Threads miss each other, you get the wrong answer. But what if it gets worse? What if the threads don't just miss each other, but they get stuck waiting for each other forever? Well, that leads us to an even scarier problem: deadlock. Yep, a deadlock. The name is pretty fitting. It's what's called a liveness failure, meaning your program isn't dead, but it's not making any progress either. It's just frozen. It's like a digital standoff where multiple threads are locked in this deadly embrace, each one holding a resource the other one needs and absolutely refusing to let go. Your whole application just grinds to a halt. Think of two workers on an assembly line. Worker 1 grabs the screwdriver and says, okay, now I need the wrench. At the exact same moment, worker 2 grabs the wrench and says, great, now I just need the screwdriver. You see the problem? They're stuck. Worker 1 has A and is waiting for B. Worker 2 has B and is waiting for A. Neither one is going to budge, and they will wait there forever. So, wow. Race conditions, deadlocks. This sounds like a total nightmare, right? How on earth is it even possible to write correct software that does multiple things at once? Well, the good news is there are clear strategies. There are rules for taming this chaos. The goal, the holy grail, is to achieve what we call thread safety. And it's a simple concept. It just means your code behaves correctly, period. No matter what crazy, unpredictable order the operating system decides to run your threads in. Your code has to be robust enough to handle that Starbucks-style bad luck every single time. Okay, so the first strategy is the most direct one. Just make the threads take turns. You do this with a tool called a lock. It's like having a talking stick for a piece of shared data. Only the thread holding the stick is allowed to touch it. Every other thread has to wait. This completely prevents those check-then-act race conditions by making the whole operation atomic, meaning it's all one uninterruptible step. But an even more elegant strategy is to avoid the fight altogether. Don't share your toys. If there's nothing to fight over, there's no fight. You can do this in two key ways. First, immutability. Make it so your data can never be changed after it's created. If it can't change, who cares how many threads read it at once? The second is thread confinement. Just keep the data private to a single thread. If no other thread can even see it, there's no need for a lock. The problem just vanishes. And finally, strategy 3, and this one is huge. Don't reinvent the wheel. Seriously, writing correct concurrent code is incredibly difficult, but for many common situations, experts have already built bulletproof, thread-safe components for you. They've done all the hard thinking and testing, so you don't have to. Use them. So, to sum it all up, we've got a toolbox for managing these risks. You see a potential race condition, you use synchronization to make threads take turns. You're dealing with shared data that changes? Well, either stop sharing it or make it unchangeable. And to save yourself a world of headaches, just use the tools built by the experts. So, why does all of this matter so much right now? More than ever before? What does this mean for how we build software going forward? Because, as the book makes crystal clear, threads are absolutely everywhere. You might think, oh, I don't write any advanced multi-threaded code, but here's the reality. It doesn't matter. Even if you never explicitly create a thread yourself, the frameworks and libraries you depend on are creating them constantly on your behalf. There's really no escape. And this leaves us with a final, really important thought. In a world where even our phones have multiple processor cores, is understanding concurrency still some optional skill for specialists? Or has it become an absolutely fundamental, day-one requirement for every single person who writes code? Something to think about. Thanks for joining us.